What's up guys, and welcome back to the channel. So one interesting thing about electric cars is a phenomenon that's colloquially known as phantom drain, which is a circumstance where if you leave the car unattended for a long period of time, you'll notice that the battery charge level drops. If you're wondering why this happens and what you can do to reduce its effects, then stick around because that's what we're going to explore in today's video. Let's get started. All modern electric vehicles use what's known as lithium-ion battery technology, which fundamentally is the same type of technology that you might find in your smartphone, laptop or tablet. The reason why lithium-ion battery technology is so much more popular than alternatives such as lead-acid or nickel-cadmium batteries is due to the fact that lithium itself is the lightest of all metals, meaning that lithium-ion batteries have the highest gravimetric and volumetric energy densities of any commercially available rechargeable battery systems. But of course, lithium isn't without its troubles, one of which, of course, is the phenomenon known as self-discharge. To fully understand self-discharge, we're going to need to examine the basic principles by which a lithium-ion battery works. Fundamentally, a lithium-ion battery consists of a positive and negative electrode separated by a substance known as electrolyte. When the battery is being discharged, lithium atoms within the negative electrode become oxidized, meaning that they lose the electron from the outermost shell of their atomic structure. Since electrons carry a negative charge, when they leave their parent atom, the remaining atom gains a slightly positive charge and becomes known as an ion. The free electrons now create a flow of electrical current, which exits the battery through its negative terminal and into the circuit to which it is supplying power. Inside the battery, the remaining lithium ions migrate through the electrolyte towards the positive electrode. The electrolyte substance itself is specially designed to facilitate the free passage of lithium ions through to the positive electrode, while simultaneously preventing the flow of any electrons within the battery itself. Once the electrons have flowed through the connected circuit, they will return to the positive terminal of the battery. When these electrons come into contact with the positive electrode, they will cause reduction of the electrode material, which enables the awaiting lithium ions to become interpolated within the electrode material itself. When charging the battery, the opposite reactions occur, causing the lithium ions to flow back across the electrolyte and into the structure of the negative electrode. So at face value, this seems like a pretty simple process, right? Lithium ions flow from one side of the battery to the other, emitting free electrons in the process, which power any connected circuit. So what causes the battery to lose its charge over time? Well, fundamentally, this comes down to the effect of chemical reactions between the electrodes and the electrolyte material. If we go back to our animation where the battery is being charged, you'll note that the lithium atoms become embedded within the material of the negative electrode. However, when a large number of lithium atoms become embedded within the electrode, such as when the battery is at a high state of charge, its reactivity with the surrounding materials increases significantly. This increased reactivity results in the occurrence of electrochemical reactions between the electrode and the electrolyte, in which lithium atoms become permanently embedded within a thin layer of material known as a solid electrolyte interface, or SEI. Since lithium atoms facilitate the flow of electrons from our battery, the more lithium atoms that become permanently embedded within the SEI material, the less will be available to supply these free electrons. Compounding this issue are two other factors, voltage and temperature. If you charge the battery using a very high voltage, such as during prolonged high-power charging, this can cause the positive electrode material to become highly reactive, resulting in oxidization of the electrolyte material, which can cause further deposits of reaction product along the surface of the negative electrode. High temperatures further aggravate these reactions, which ultimately result in both a capacity loss in the battery through a depletion of lithium inventory, in addition to the buildup of micro-shorts caused as a result of excess material buildup on the surface of the negative electrode. These micro-shorts can create leakage paths for electrons to flow within the battery itself, resulting in a further loss of energy. So now that we have an understanding of the science, we can start to make some deductions about the self-discharge behavior of a lithium-ion cell. If the state of charge of the battery is close to 100%, then the negative electrode will be saturated with lithium atoms, resulting in increased reactivity and a higher probability for energy dissipating electrochemical reactions to occur. Similarly, if the battery is at a high temperature, the reactivity of both electrodes is further increased, compounding the rate of self-discharge due to the processes of SEI material buildup and microshorting outlined previously. Okay, so that covers the theoretical aspects of self-discharge, but what does that mean for us in the real world? Well, let's take a look at some data. Here we have a table representing the self-discharge rate of a standard lithium-ion battery cell across a temperature range from 0 to 60 degrees Celsius. If we take a battery that is charged to 100% and examine its discharge rate over a 1-month period, we would see a total discharge of 6% at 0 degrees, 20% at 25 degrees, and 35% at 60 degrees. Now, if we take the same battery, but this time with a starting state of charge of between 40 to 60%, we see a range decrease of 2% at 0 degrees, 4% at 25 degrees, and 15% at 60 degrees over the same 1-month period. From this data alone, it's clear that battery state of charge and temperature have a significant impact on the rate of self-discharge, and it's something that should be kept in mind if you're ever thinking of leaving your car unattended for any prolonged period of time. However, the story doesn't stop there. Battery chemistry alone only accounts for a small part of the overall impact of phantom drain, so let's examine the next culprit. In a Tesla Model 3 battery pack, there are 4,416 individual battery cells, each just a bit larger than the size of a standard AA battery. That's 4,416 batteries, each with their own electrochemical characteristics and behaviours that need to work together to provide a consistent energy output to the connected systems. In order to do this, each Model 3 battery pack has what's known as a Battery Management System, or BMS. In addition to monitoring the status of the battery cells themselves, the BMS also regulates power output to other electrical systems, such as the 12-volt battery, power converters, and charging systems. As you can imagine, performing each of these functions comes at a cost in terms of energy, which manifests itself in the form of phantom drain when the vehicle isn't being used. So what can you do to limit the impact of this phantom drain? Well, let's take a look at the energy consumption statistics for some key vehicle functions which are active during standby. First up is Sentry Mode. In 24 hours of standby, the car consumed 31 kilometers of range, which equates to a range loss of approximately 1.29 kilometers per hour. Next, we have the cabin overheat protection feature. When enabled, the car lost 7 kilometers of range over the course of 24 hours, or approximately 0.29 kilometers per hour. Next, we have Summon Standby, which consumed 2 kilometers of range over a 24-hour period, or 0.083 kilometers of range lost per hour. Unfortunately, it's not possible to enable both Sentry Mode and the cabin overheat protection feature at the same time, so I was not able to obtain a reading for when all three functions were enabled simultaneously. However, I was able to conduct a test where both Sentry Mode and Summon Standby were enabled, and in this case, the car lost 34 kilometers of range over 24 hours, or approximately 1.42 kilometers per hour. Finally, if we compare these values with our control case, in which none of the features were enabled, we see that the car still lost 2 kilometers of range over a 24-hour period, which is quite interesting. Based on this information, we can see that many of the active standby features such as Sentry Mode consume a considerable amount of energy while the car isn't being used. But let's break it down even further. If we look at the battery percentage indicated by the battery icon on the touchscreen and compare that with the corresponding estimated vehicle range value for that battery percentage, we can extrapolate the range that the car would get on a 100% charge, which in this case is 479 kilometers. Since we know that the battery pack size is 75 kilowatt hours, we can then calculate the kilowatt hour energy consumption per kilometer, which works out at 0.156 kilowatt hours per kilometer. Using this value, we can then calculate the amount of energy used by Sentry Mode. Since Sentry Mode consumes energy at a rate of 1.29 kilometers per hour, if we multiply this by our kilowatt hour per kilometer number, then we get a value of 201.24 watt hours. Now, if we divide our battery pack capacity of 75 kilowatt hours by the energy consumed by Sentry Mode, we can see that it would take just over 372 hours, or roughly 15.5 days, to fully discharge the battery with Sentry Mode enabled. So if you are thinking of going on a 2-week holiday and leaving Sentry Mode enabled, then you might want to consider this going forward. Tesla do have a built-in safety feature which automatically disables all active Sentry Mode features once the car battery percentage drops below 20%, so a circumstance where you'll ever come back to the car and the battery level is totally depleted is quite unlikely. Before we move away from active standby features like Sentry Mode, there's one final thing that I'd like to cover which mightn't necessarily appear obvious, and that is how much it actually costs to use them. If we do some quick maths based on the energy consumption statistics for Sentry Mode alone, assuming you charge your car at home at a per kilowatt hour cost of 17 cents, leaving Sentry Mode on for 12 hours every day will cost about €150 every year. This was certainly an eye-opening statistic for me, since I used to just leave Sentry Mode on by default, but now that I have a cost figure associated with it, I certainly think twice about whether or not I actually need to enable it. If you're the type of person that never uses any of these active standby features, then you'll notice that our control case showed that the car lost 2 kilometers of range over 24 hours. This is quite interesting, since you'd think that if there are no active standby features enabled, then what else could be draining the battery? And this is where the Tesla smartphone app comes in. Anytime you open the smartphone app, a request is sent to your car to wake up some key systems which report on details such as battery status and cabin temperature. Even if you don't do anything in the app itself, the car will still remain in an awakened state so it can receive and respond to commands as and when they come, which of course uses a non-negligible amount of energy. This issue is further exacerbated if you use third-party applications such as Teslafy, since these apps continuously poll the car for information at set time intervals, which uses even more energy. Also, if you use quick access widgets on your smartphone, these can also generate a large number of calls to wake up the in-vehicle systems. So be sure to keep these details in mind if you ever think that you're going to leave your car for a long period of time. Finally, our last topic of the day is related to this little icon right here, the snowflake icon. If you leave your car parked out in the cold overnight, then you might wake up to a circumstance where you'll see this little snowflake icon on your battery icon on the touchscreen. Depending on the severity of the cold, you'll also notice that the power meter underneath your speedometer will have the upper sections dotted off to show you that both your regenerative braking and your available power are reduced. So why does this happen? Well, if we go back to our chart outlining the rate of battery self-discharge versus temperature, you'll remember that we said the reactivity of the electrodes increases with temperature. So naturally, if the temperature drops to very low levels, then the rate at which electrochemical reactions can occur within the battery pack is also reduced. The amount by which this power is reduced is reflected both on the battery icon itself, as indicated by a layer of unavailable blue battery capacity, and by the dots of unavailable power on the power meter. However, it's important to note that this doesn't mean that all of this energy is lost. Instead, it's just a reflection of the slower rate at which power can be delivered from the battery pack due to the slower rate at which electrochemical reactions are occurring. As you can see in this example, one morning my car showed that it had 147 kilometers of range with the snowflake icon, but later that day, once the battery had warmed up, the range went back up to 160 kilometers. So, in summary, what did we learn about phantom drain? Well, we learned that factors such as temperature and battery state of charge both have a significant influence on the rate of self-discharge of the battery cells from an electrochemical perspective, where high temperatures and a high state of charge contribute to faster rates of self-discharge. We showed that prolonged use of high-power charging can increase the likelihood for the formation of microshorts and a depletion of overall lithium inventory, which reduces both battery longevity and performance in the long term. We learned that the active standby features such as Sentry Mode and cabin overheat protection can consume a considerable amount of energy while the car is not in use, and should be taken into consideration whenever you intend to leave your car unattended for any prolonged period of time. And finally, we saw that cold temperatures can limit the rate at which power is delivered from the battery, which can temporarily reduce the amount of available vehicle range and performance until it reaches a more optimum temperature. So that's it for today's video. I hope you found it useful and informative, and if so, be sure to like and subscribe to the channel for more videos like this every week. As always, if you have any questions, be sure to let me know in the comments, and until then, I'll see you in the next one.